So friends, today we'll deal in one of the very interesting things which has been responsible for lots and lots of research because of heat transfer has been a subject of much importance, and the heat transfer takes place through three different mechanisms: conduction, convection and radiation. In conduction, the heat is carried, maybe if there is a rod, from one end to the other end, okay, by means of a temperature difference, and it parts of they transfer heat from one part to the other part, okay. So conduction is the mechanism of transfer of heat between adjacent parts due to a change in temperature. In convection, my teacher, who was a hockey enthusiast, and he used to like Inamur Rahman, who was one of the great hockey players, or maybe Dhyan Chand also, okay, who was greater. What they used to do is, from one side, from our side of goal, they will take the ball and carry the ball here and there, and then they take it to the other goal and shoot, and the goal will happen. That means in conduction there is a material transfer. In convection there is a material transfer, and the transferred material carries the heat with it. In conduction there is no transfer of material, and in radiation, of course, neither things takes place. It is radiation. One of the radiations that we know about is the radiation from the sun, also from the moon, which is a reflection. It's not a source of radiation, but it reflects light which falls on it to the earth. And between the sun and the earth, there is a lot of material-less space, something called nothing, which we call vacuum. Almost vacuum exists there. So number of molecules in that space is very, very small per meter cube. So that is how the radiation takes place, and there are other things, examples there. So conduction, the mechanism of transfer of heat between adjacent parts, the transfer of the heat between adjacent parts of an object, of a substance, due to a change in the existence of a delta T, that is, and it flows from high temperature to low temperature. Normally, we find that the metals and alloys, they are good conductors, gases are bad conductors, and liquids are in between. In Arabic, bayyan, okay, in between, okay. Now, before I go for other things, let me introduce to you an arrangement by which we can study the heat transfer. There are two large reservoirs of temperature, Tc and Td, which are maintained temperatures. To maintain the temperature, because the heat will be transferred like this, from this end to the other end, through this length L, through this area of cross section A, and the material will also matter. So you have to continually supply heat over here, and heat, there should be arrangement that the heat goes out of the reservoir. How much heat? The same amount which enters over here, the same amount after transfer from this end to the other end of the rod under consideration, and then it is given out to the surroundings. The area of cross section is the same, okay. These are large reservoirs maintaining the temperature and Tc and Td respectively, which I have written. The temperature is maintained and also the temperature is maintained over here, and Tc is greater than Td. Okay. Then what we wait is that a steady state flow by conduction takes place, which we can manage and find out with the help of inserting some thermometers here and there and monitoring the temperature, that the Tc value and the Td value don't change. So this kind of an arrangement can be done. Okay, it's not very difficult. Okay, now I've just shown that the sides of this rod, I've just taken a, what is it called, the cross section, okay, in the 2 dimensions, and these are what we call insulators. So this rod is completely insulated from here, so that there is no loss of heat due to radiation, etc. So whatever heat enters over here, that heat should go to the other reservoir by this procedure, and the procedure is fits the description of conduction, which is the mechanism of transfer of heat between adjacent parts due to a maintained temperature difference. Okay. Now let us see, what is this? There is a time rate of heat flow in a material for a given delta T, and this is what we call H. Okay, time rate of heat flow in a material for a given difference of temperature delta T. As I told you, the sides of the wire are fully insulated, no heat exchange between sides and surroundings takes place. So now the heat current, the rate of flow of the heat, which is also called heat current, okay, the heat current, it is found experimentally by observation, by doing experiments with a number of materials, a number of rods, number of reservoirs, etc., etc., and making a change in the value of A. So the area of cross section of the rod is a variable. Also, you can maintain A and the length and change the Tc minus Td. That is, the temperature difference is also changed. So I can say that this is Tc minus Td. Interestingly, it's very simple to imagine that if the length of the rod is less, then there is a quick transfer of heat, and as the length of the rod is increased, so the transfer will be less and less. So we find that there are variables A, there is a variable Tc minus Td, and there is a variable which is L. These factors, the value of H depends. Now, as I told you in the beginning, for the case of the force between two masses or two charges, as I introduced multiple things there, because the source over there is a point source, and so there is an inverse square law which exists over there. So what we find is that if we use what is called the principle of mathematical consistency, then I can write that H is proportional to the product of all these variables, A, Tc minus Td, and L, 1 upon L. Okay, so which gives, naturally, because these are the only things, then we obtain a relation that the heat current H is equal to, like all cases, a constant of proportionality capital K into A into Tc minus Td divided by L, where this K is called the coefficient of thermal conductivity or simply thermal conductivity. So we can study, we can tabulate the coefficient of thermal conductivity. Of course, the temperature etc. The pressure etc. had to be defined, because the pressure also may play a role. Okay, so those things, those data must be there. So I have the heat flow per second is equal to, in the steady state, capital K A Tc minus Td over L. So H is equal to K A Tc minus Td upon L. These are variables. Okay, and you see that for a given set of these things, if that is constant, then K will determine as to how rapid is the conduction. Greater the K, more rapid the conduction, and smaller the K, less rapid the conduction. It's very simple. Okay. Now let us take some examples. For example, for cooking utensils, often there is a copper coating at the bottom, and this copper coating ensures that the heat from the flame is equitably and quickly transferred to the main material of the utensil, and cooking is easier for us. Similarly, there is another example of roofs, where we have a concrete first, and the concrete is laid, and thereafter we have a kind of a mud huska, and then there is a tile. The concrete is, if there is no mud huska and tile, which is a kind of an insulating thing, then the heat transfer from the roof to the ceiling and therefore to the rooms where we live in, that will be a bit faster. Okay, as compared to the case of mud huska. So it's insulating also, and it's kind of putting this thing, okay, resistance to the transfer of heat through that plate, which we call the concrete plate. Now, if we study the value of K, which is given is in joules per second per meter per Kelvin, or watts per meter per Kelvin. The value that I have given over here is ranging from the silver to copper, aluminum, brass, steel, plumbum and lead, and mercury. Then insulating brick is 0.015, concrete is 0.8, which is more as compared to the insulating bricks. Earlier the houses used to be made with bricks on the rooftop, so it was they were better as compared to the concrete houses that we are subjecting us these days. Water, our friend, has got a conductivity or coefficient of thermal conduction 0.8, and air has got the least. So it is just to give you a glimpse of that. Okay, now we are going to do an exercise where I want to calculate the temperature of a steel copper junction in the steady state of the system that I will just shown. I'll explain to you. The length of the steel rod is 15 centimeters, that of the copper rod which is making a junction with the steel rod is 10 centimeters. One side there is a furnace, the other side is an ice box. The furnace temperature is maintained at 300 degrees Celsius. This is one reservoir, and this is the other reservoir. It is ice box. It is 0 degrees Celsius. Okay. The area of the steel is double the area of the copper. That can be a variation. Also, we are given the steel value of K is 50.2 and that of copper as 385 watts per meter per Kelvin. Now, the situation is like this. Okay, this side I have a steel rod, and this side I have a copper rod. Okay, the length of the steel rod is more as compared to the copper rod. It could be otherwise. There is no problem. The area of cross section of this steel has been taken twice that of the copper. It could have been otherwise. It could have had any kind of a relationship here. The furnace temperature is not important. That could have been anything, and the ice box, of course, the temperature will be equal to 0. But if there is another absorber at the other end, that can be defined. Okay, so this is what we are going to do. Okay, to explain this situation. So this is the problem that we just defined, and I have tried to draw a schematic diagram where one of the reservoirs is 300 degrees Celsius. This is a furnace, and an ice box over here, 0 Celsius. Could be any two reservoirs. And between those reservoirs there is an exposure here and also an exposure here to the reservoirs. Okay, I have shown according to the data that has been given to us that the steel rod is thicker and longer. Okay, and the copper rod is thinner and shorter. In fact, I will make the application of this H is equal to Ka Tc minus Td upon L. Okay, and under the steady state, I can have n rods of n materials. So there will be several junctions, and the junction temperatures we can find out by a similar kind of arrangement using this relation. So it doesn't matter. I can vary these are the variables. You can see the material is variable, the temperature difference is a variable, the length is a variable, and in this case we also have the value of the K is also variable. What is not variable in this particular case, where we have arrangement of several rods in series with each other, is that the same amount of heat, so heat taken per second anywhere, or heat flowing, or heat current will be the same anywhere at any point of the steel rod, and thereafter any point of the copper rod, etc., etc. Okay, and we can calculate the value of T here at the joint value of the T anywhere here, and we can take several rods of different materials, of different areas of cross section, okay, and of different lengths. So in this very simple case, where I have only two rods, one is of steel and the other is copper, 15 centimeters, 10 centimeters, that can be made variable. No problem. 10 centimeters. Even steel and copper, that can also be varied. No problem. No problem at all. Furnace temperature can also be changed. This can be made variable. This can also be made variable. No problem. So the values of K values, they can also change. And the arrangement is very simple. The kind of the process that you do is what has been depicted over here on this particular case. First is the case of steel and the other is the case of copper. So whatever heat is coming into the steel, that flows in the steady state and then it goes to the copper, and of course the temperature over here at the junction we have taken T, and this is what we are going to calculate. When we substitute the values of K1, A1, L1, K2, A2, L2, okay, then we can carry out that mathematical tidbits, and then in this particular case we find the value of the temperature of the junction to be equal to 44.4 degrees Celsius. There is another possibility, and another possibility is that you can be given 2 rods or umpteen rods which are joined like this. They may have an area of cross section, length is the same, area of cross section may be different. This is 1, this is 2, maybe there is 3, there is 4, and the heat is injected from one end through a reservoir and is injected to another end through another reservoir. Okay, we can have a temperature here which can be Tc, which can be Td, and here I can have K1 and I can have K2 as the conductivities for the 2 rods. But the key is that steady state, in the steady state which is achieved, rate of flow is the same at every point along the length of whatever combination is there. So that is another way of doing things, okay. And here they have shown steel and copper in a question like what you call MCQ, okay. In a question like that, one can provide you the ratio of K1 and K2, etc. You can also provide the ratio of A1 and A2. They can also provide the ratio of L1 and L2, and then ask you as to what will be the temperature, sorry, not this temperature but this temperature, or what kind of a variation is expected in this kind of temperature. So with that, I think I have done justice to the conduction part, okay. And it's very interesting kind of questions are there which you must, because whenever an examiner wants to set a question, MCQ or otherwise, this simple relation is taken into consideration, and then they can ask which is what, or rank them like that, 1 2 3 4 1 3 2 4, etc., etc. So these kinds of questions, and one of the things which I would like to tell you is very interesting, that we the teachers, we make or construct a question, okay. There is the restriction that we have, and the restriction is of print media. That is not a restriction to you. You have all the freedom to make variations. So the beauty of a good student that you are is build up questions, to create questions. Okay? And once upon a time when I was a teacher, I had a sessional test to take. And that was for maybe 10 or 20 marks for the sessional examination. Okay? And the students came prepared for an examination paper. And I had no examination paper in my hands. And I had no chalk in my hands. Okay? And I am looking at the boys, there were boys only in that class, and the boys are looking at me. And then I told them, look friends, I want you to make a question paper, okay, for say 10 marks. Write the question paper, leave the paper, okay, and I will assess what you know about the subject. Finally, some of the students, after trying to make some questions, to prepare some questions for the examination that they had to conduct for themselves, they told me, sir, please, okay, you ask questions and we will answer. We cannot frame questions because that instinct which is required in a normal student, in a less than normal student, or better than normal students, is what instinct is essential is that they should be able to ask questions, they should be able to make variation of variables, and naturally in between they can exchange these questions and try to find out the answers. If you have some questions like that, where you have felt any difficulty, I can only help you. And I can help you through the comment section that we have, and I will try to answer you. Thank you very much for being with me. Thank you again.